Hello, everyone. Welcome. Thanks for joining our diagnostic training session today. And what you're about to see is a pre-recorded training session we did over in the United States. But be assured that a lot of the material that we cover is really applicable to any automotive application. So just be aware that yes, it is a lot of North American vehicles, but they will apply a lot of the same principles apply over in the UK as well. Now, if you do have any questions, if you're watching this during the premiere, you can just leave it in the chat. We'll be monitoring live chat. If you're watching this after the premiere, then just feel free to leave a comment underneath the video and we'll get to those as we can as well. So my name is Jason Gabrenas. I'm one of Snap-on's diagnostic technical trainers. I've been in the training department since 2013, traveling around North America, helping techs and shop owners get the most out of their diagnostic equipment. Before I did that, it was a couple years as a diagnostic sales rep at Snap-on, so I had 30 different franchisees I worked with, as well as the shops that they serviced, in order to help everyone get the most out of their diagnostic needs. Then before I did that, it was 8 years at Subaru. So I worked in a dealership, and over time, I guess, just became the default diag guy in the shop. So I always ended up having the drivability problems, the intermittent problems, the weird wiring problems that would show up on those cars. And that's really where I cut my diagnostic teeth, was trying to figure out all those weird head scratcher type cars that would come into my bed. Then before that, a bunch of other miscellaneous wrenching jobs. Been a little over 25 years under hood experience for me. So our topic today is intro to lab scope. Now you may think, well, lab scope, maybe it sounds like could be interesting, right? It's something that you hear a lot in the industry. Let's use a scope to help us diagnose. And maybe you don't know where to start. Maybe you're not entirely sure. Maybe you think you'll blow up the car if you use it. Not really sure. It kind of runs the gamut there. But we do have really two different types of diagnostic tools, and they're used for two different purposes. So we think we have a scanner and we have a scope. And when I think of a scanner, I like to think of it as a really nice compass. It's going to point us in the right direction. It's going to show us where we need to look, where we need to go, but it's really only showing you the effect of what's going on under the hood. And the effect is really after it happens, right? And every effect needs a cause. So in order to find that cause, that's where the scope comes into play. It's in our component testing and electrical testing that we'll be doing. So we think about a vehicle's computer. We're going to just start with the basics as to why we would need this, and then we'll slowly grow as we go through this process in this session here. But if we think about a computer, vehicle's computer, let's think of it like a house. It's got a front door, it's got a back door. So coming in that front door is going to be all my input signals that go in and feed the computer and tell it what's going on in the world around it. So coolant temperature sensor, NOx sensor, oxygen sensor. All of these things feed their information into the PCM. Then the PCM makes some calculations, decides how the vehicle is going to drive down the road, and takes that information and spits it out the back door and gives it to the scan tool. So when you're looking at data and only using data to diagnose with a scan tool, you are only looking at that data after the PCM has already taken a look at it, processed it, and sent it back to the scan tool, right? All of that takes a little bit of time, for one thing. And the other thing is it is the computer's interpretation of what it's seeing based upon its programming. And if you've been around long enough, you know that the programming is not always all that good either. And that's why we have these things called reflashes, where we have to actually reset the computer and change the software, right? So in order to test these signals, though, we have our scan tool, which is going to hook up to the OBD2 connector. So any OBD2 compatible tool would be able to work with that. And then being able to test before that signal gets to the computer, well, you're not going to have that data stream, so you need a scope in order to test that, be able to actually check the sensors themselves and miscellaneous other things underneath the hood. There's many tests we can do. You may be thinking, well, I've been relying on data this long. Why do I need a scope? Why can't I just rely on that data? Well, it brings us back to what I was just saying. It's that interpretation. Back in the day, back 30 years ago, when we started first putting scan tools on cars, the vehicles weren't all the computer processor anyways, wasn't all that fast. And if you were lucky, maybe you had 6 or 7 data points on a car, because they weren't all that complex back then. And granted, the scan tools weren't all that complex either. So you may be thinking, well, I'll just rely on that data and be good with it. But nowadays, modern vehicles, these sensors and the way that data stream is presented to us, there can be hundreds of data PIDs that I have to filter through and look through. And those numbers can be changing 10 times a second or faster. Now, I don't know about you, but if it gets to be over 100 data points coming at me and they're changing 10 times a second, pretty hard to understand what's going on just by looking at the data. Now, of course, we have ways to filter it and customize the list and speed it up or slow down the amount of information that's there. But once again, it's data overload at this point, I think. So it's valuable. It's good to have the data so we know what the computer's thinking, but often it's too fast and too much to understand what's going on. So then, I don't know, probably about maybe 10 years later, after we first came out with our first scan tool, we had the graphing scan tool that came out maybe 5-10 years after that. And what the graph is, and there's many scan tools that can graph nowadays, it takes those numbers we were using prior and it graphs those numbers, paints a nice picture for you over time. It's a recorded history of that processed data coming out of the back of the computer. So instead of looking at numbers changing 10 times a second, I can look at the graph and see how that changes 10 times a second. Oftentimes, picture's worth 1,000 words, as they say. Now you can see trends. It's useful for that. Are things getting better? Are things getting worse? Are things just not even there? But once again, it is that processed data stream. Now there is there are some items on a car that we do need that data stream for misfire counts. That's all done internally. AF sensors, many of those readings are done internally on the computer as well. So oftentimes we do need it, but there are often times where we can also be led astray as well. So having the scope capability to be able to test a vehicle is really worth it. So if we look at this picture, this will kind of give you a little graphic representation of what I'm talking about. Top left-hand corner of the screen, that is oxygen sensor voltage on this vehicle. Reading the process data stream coming out of the computer. Here's what the computer is telling us it sees for oxygen sensor voltage. Goes up and down 45 to 855 millivolts. Now, if you look down here, this is a scope hooked up to the same exact oxygen sensor, reading the same exact voltage. And these two red boxes show the same amount of time passing. There is a big difference between these two pictures. Now, why is there a difference between those two pictures? If we see these two little dropouts right here, that scan tool, if you were just relying on scanner data, you had no hope of finding those two little dropouts. Now, why? A lot of that has to do with how I said the computer works. So the computer takes that information in, processes it, sends it out. Takes it in, processes it, sends it out. Over and over again. Every time that happens, takes a little bit of time. It may only be milliseconds, but it takes a little time to make that trip. So if you're using that, you're looking at data that's a few milliseconds old for one thing, and then once again, it's that interpretation. So being able to see that detail right at the sensor, that is also due to the sample rate of the scope. Depends on how fast am I measuring that signal, right? The high sample rate, the faster you go, the more samples you can get per second, the more times you look at that signal per second, the better the resolution of the signal is. And that's why we want to use a high-speed scope to be able to check these high-speed things. So we talk about a lab scope. What is a lab scope anyways? Really at its most basic level, the way I like to think about it is it's a window. It's a window I'm going to look through, and I'm going to see what is this component that I'm testing or whatever I happen to be testing. What is it doing electrically or mechanically or hydraulically, depending on how I'm testing it and what kind of probe I'm using. And when I'm changing the settings on that scope, maybe I change my scale, maybe I'll change my sweep time. We'll talk all about that in a couple seconds. We go live on the tool to show you how we would do that. But when I'm changing those settings, really all you're doing is changing the size of the window. Do I want to see more of this pattern on the screen? Do I want to see less of this pattern on the screen? Do I want to make my window taller so I can capture anything that goes up? Or do I want to make it shorter so I don't have that much of a range to look at? So all we're really doing is changing the size of the window. You're not changing the signal itself. You're not going to damage the vehicle by changing any of these settings. And often people say, well, how do I know what the settings should be? There's a couple ways we can learn that information as well. But even just if you don't know, you can always change the setting and see what happens. Right. So we'll walk through a couple of these examples now. Just wanted to give you that real quick overview of why we would even want to use a scope nowadays, and the way things need to be tested nowadays. Absolutely, it's a necessity, really. So on our tools, on Snap-on tools, so this is a Zeus here, Varus, Modus, Triton, any of those tools. The Vantage would also have these scope and meter, just a matter of how many channels they have, depending on what the tool is. So if I go into my scope and meter, and as I said, this is a 4-channel tool, so this is a Zeus. So we have the lab scope, which we'll talk about in a second. We also have an ignition scope, which actually we're going to talk about a bit next week. A little preview next week. We're going to talk ignition for techs. We also have a graphing meter and a digital multimeter. So actually, I don't spend a lot of time on these other meters. So let's take a second to go in here. So if I go into a digital multimeter, that is just like the digital multimeter you probably have sitting in your toolbox, right? It's going to read in a digital display. So let me just show you. Let me go into volts. Any of these options it'll display, and it displays it in a digital reading. Now it only samples, there's that sample rate thing again. It only samples a certain number of times a second, right? So it's going to sample slower. It's going to read that signal slower. So if I make a change, like I just really quick disconnect it, you didn't even notice that I disconnected that, did you? Disconnected it again. Ooh, it kind of caught it. It dropped by 0.4 of a volt. All I'm doing is unclipping my alligator clip here. And we see how, since it's not sampling very fast, if I do it really quick, it barely moves, right? That would be a 0-volt dropout in computer world, but it really doesn't react that fast. All right, so that's digital voltmeter, still used for some things, reading ohms, continuity, etc. But for catching really quick glitches like that, definitely not fast enough of a sample rate. So then after that, we can take the digital meter. If we want to go a little bit faster, we get to a graphing multimeter. And what does a graphing multimeter do? Well, it does the same thing our graphed data does. It takes those digital volt numbers that we had before, or whatever we're reading, those digital numbers, and graphs them over a period of time. So let's go to volts DC now on a graphing meter. Now we see that it starts coming across the screen. And if I drop it out, you can see those dropouts a lot more than we had them before, right? So I got, maybe about 5 volts going in, and then it just drops out every so often, every time I disconnect it. So I can catch a glitch faster by doing it this way, right? And the sample rate that this is at, we're looking at a 10-second window, right? So this still isn't as fast as a scope would be. So we're looking at 10 seconds at a time on the screen. We could go in a little closer if we wanted to, but that is good for catching those quick little glitches that come out if they're long enough. Now, if we're looking at networking, CAN bus, right? CAN bus, the spec on CAN is each of those there's little data packets that we'll see. And I think we'll have enough time to get to a CAN pattern at the end here. But if we look at the data packets on CAN, there's a spec for how short they can be and still be considered a valid piece of data. And that is a millionth of a second long, 1 microsecond. So if I lose that 1 little millionth of a second glitch, I won't be able to catch it on that graphing meter because it doesn't react fast enough. The only way I'm going to be able to catch it is with a scope. Now, a snap-on scope, 1 channel, 6 million samples per second, and then we divide by how many channels we're using. So if I'm using 2 channels, it's 3 million, and so on and so forth. So at max, with 1 channel going, that is 6 million times per second, it is looking at the signal for a glitch or a dropout. Now, you see how I'm undoing the clip, and that signal is not moving much because of the sample rate. We're looking at a teeny tiny bit of time now. We're only looking at 10 milliseconds worth of time passing. If I was before looking at 10 seconds worth of time. So that's way more time passing, and those glitches are a lot longer. So I don't necessarily catch it. Now I could go out. Let's pull a few glitches in here. And I might be getting ahead of myself a little bit too, but that's okay. Go through here. All right, so I got a couple glitches in there. Now you didn't see them on the screen, but what if I wanted to find them? So I can go out and use my zoom function. So if I hit zoom, hopefully we caught it. No, we didn't catch it actually. Okay, let's try that again. I didn't hit stop fast enough. I gotta be quicker on the drop. All right, there we go. So we'll get that rolling. Do a little bit of that. Now I'll go a little bit faster. There we go. That should catch it. All right, there we go. So there's all my glitches right there. These are all my little glitches where I released the clip. So I can just go in here, I can zoom in, get a little closer, see what actually happened. Now you can see how it went slowly. It curved down, right? So we can see these details. And these are the details that we want to see when we're going in and interpreting different patterns, right? So this is high level, how we would use it. Now let's get down a little bit more into how we actually would set this up and how we would make it work, right? So we want to be able to catch high speed glitches is the point we're trying to make here. So let's go and pull up a simple, this is a 5-volt square wave pattern, just a repetitive 5-volt square wave on the screen. How do I know it's 5 volts? Because I know it's a 5-volt simulator, but how else would we know that it's 5 volts? So we can look on the left-hand side to our scale, and we see the peak is about halfway between 0 and 10, so let's say 5 volts. Now we will be able to measure this as we get a little bit further. But what I'd like to do is I'd like to change some of the settings on the scope to be able to see this a little bit better, because right now to me that's a little bit small. That's a little hard to see what's going on. I want to see it a little more in detail, so I want to get it, make it bigger on the screen. Now, I wouldn't necessarily use a zoom function for that, but I would change my scale to do the height. So if I go down here on the bottom right, this allows me to change my settings. It goes through 3 screen views. I have my just the scope, I have the scope with measurements, and then I have the scope with the settings. So I want to be on my settings. If I wanted to add additional channels, that's in the first column, that's these eyeballs. Want to add channel 2, click channel 2. Want to add channel 3, click channel 3, and so on and so forth, right? So I can go through that and add additional channels, turn them on and off. Right now, we're only concerned about the one. So let's do that. Channel 1's on. First thing we have is probe. So if I want to change what I'm looking at, in this case, we are looking at voltage, so we'll just leave it as a test lead volts, but it could be a vacuum probe, pressure probe, low amps probe, or an ignition probe hooked up here. We would select the corresponding probe that we're using and then hit back, and then we'll be able, it will change the adjustment in the scope to be able to read that. Next one is peak detect. What that does, if I want to see extra detail in my signal, that'll remove any filters, any buffers, anything, and it sets it to a maximum sample rate. So that is my 6 million samples per second right there. We can see I got a lot of noise that's getting picked up on the screen there as well. So I'm actually going to turn that off for now. Filter does, I guess, the opposite. It filters out any noise that you may get in your signal there as well. So if you have a really noisy pattern and you want to make it a little smoother looking, filter will filter that out. Inverted does exactly as it says. It inverts the pattern. So right now I have a positive 5 volts. If I hit inverted, I will now see a negative 5 volts. Now it's hard to see with a repeating square wave pattern, but it goes from 0 to -5 instead of 0 to +5. I'm going to flip that back over. Coupling AC, what that does is if there is some sort of an up and down AC type component to the waveform, it will take it, it will strip it out, strip out any of the average and just amplify the differences, high to low is what that does. And then calibrated would only be if my probe needs to be calibrated, and that's a pressure probe, and ohms, we would be able to calibrate those. And then we have scale. So scale is going to change the vertical height. Remember how I talked about this as a window. So it's going to change the height of the window. Right now it's set to 100 volts. So if we look on the left, it's -10. 80 is the highest we see. Next one's 90. So it's -10 to 90. That's a 100-volt range. If I look over here on the right-hand side of the pattern, I can slide that up and down on the screen if I need to. Now I'm going -30 to +70. Still a 100-volt range. It just changed where 0 is on the side of the window. So I'm going to bring this all the way down. Bring it down so 0 volts is on the bottom. All right. I don't want to change my scale. So I'm going to change that 100 down. Well, I know it's a 5-volt scale. So if I set it to 5 volts, it's going to fill up my screen, right? So I got 0 on the bottom, 5 volts at the top. I always like to have a little bit extra over the top, just in case something goes higher. I want to be able to see it. So in this case, the next one up from 5 volts is going to be 10 volts. So I can go there. And now I have that extra 5 volts of headroom. So if I got a 6-volt spike or a 7-volt spike, I'd be able to see that and not have it chopped off the top of the screen. I can still move this around. If I wanted to center it on the screen a little more, we can do that as well. Then we have our sweep time. So as I said, right now we're looking at 10 milliseconds worth of time passing. What if I wanted to get in a little closer? If I wanted to get in, say, 500 microseconds. So that's 500 millionths of a second. That is a very short amount of time. And I can only see maybe half of that pulse. Let me move this over a little bit more. We'll talk more about this trigger in a second. Yeah, I can just see a full pulse plus a little bit extra on the screen. So I'm only looking at 500 microseconds passing. If I want to go a little further out, maybe I want to see 100 milliseconds. That's 10 times faster or 10 times more information on the screen than where we started, because we were at 10 milliseconds. Now we're at 100 milliseconds, right? So now I see a lot more time passing, right? So all we do is just adjust it so we can get it on the screen to where we can see it and we can analyze it and measure it. So I like that 500 microseconds in this case. Okay, so now I have one pulse on the screen. I'm going to measure this pulse. Once I get a pattern on the screen, you probably want to measure it to see what's going on, time-wise, voltage-wise, that sort of thing. So once I do that, I'm going to go up to my cursors, click show, click back, and now I see I have these two white lines on the screen. So I'm going to stop this recording because we can't measure it while it's actively recording. So we need to stop the recording. So I'll do that. And then, of course, we get a little bit off on my pattern here. So that's fine. I'll just pick another one. Oh, there we go. That'll work. So I'll take cursor 1, put it here. Cursor 2, put it here. And we'll see how long that pulse is. Got a little bit of a lag here right now. There we go. See how long that pulse is and how many volts we have going on this pulse. So if I pull up my measurements, which are going to be down here on the bottom 2 times, cursor 1, we see we have a yellow line and we have a white line, and we have cursor 1, cursor 2, and delta. Cursor 1, where this yellow line is going to be where vertically do these 2 lines meet. So if you see, it's right there in that little pinpoint right before it goes up. The voltage measurement is 0.01, 1/100th of a volt. Pretty darn close to 0 volts. If we look at cursor 2 is reading 5.01 volts. So that's the other side, right? So it's 5 volts on the high side. Delta will give us the difference between the two. So 0.01 to 5.01, that is a 5 volt even difference between the two. So it does the math for you as well. You also can read time right here. So if I look from here to there, how long is that pulse? Well, that pulse is, the first cursor is at 103 microseconds. That's there. So 0 to 100. Second one's at 480. So the difference is going to be what's in between, which is what we want to see. 377 microseconds. So it's 377 microseconds long is how long that pulse lasts. 377 millionths of a second. With the high sample rate, we can see something that occurs that quickly. If I had a glitch that was a couple microseconds long, only maybe, let's see, 14 microseconds. That's 14 microseconds right there. 14 millionths of a second. I can still catch that glitch using the scope. And I'm not even all the way down as fast as we can go down to 50 microseconds on one channel. So the detail that you can get with a scope versus getting out of a scanner, night and day. Huge difference. All right, so that is a basic pattern with some basic setup. Let me change my pattern here and go over to this guy right here and see what we get. All right, so I can barely see what's going on the screen, right? Over here on the right-hand side, I see this little square or right angle. I'm not really sure what I'm looking at. So I guess that means I need to change my settings, right? So I'll go to my settings screen. Let's see, time-wise, let's get a couple of this on the screen. Let's go up to, let's say, 100 milliseconds. There we go. We got a couple things going on there on the screen. I see 3 squares, but now they're off the top. So now what do I need to do? Well, I'm going to go and change my scale. So let's go to scale. Let's set it to, say, 50 volts. See where that ends up. That's pretty close. That's pretty close. Bring that down a little bit towards the bottom. There we go. So I have 3 of these patterns on the screen. That's looking a little better. Now I just want to see 1. So that means, well, I got to change my sweep a little bit closer now. So I'm at 100 and I can see 3. So let's go down to 10. There we go. Now it's way over there. Now that it's on the screen, I get it contained height-wise. I almost have it contained width-wise. This is where that trigger point we see on the screen comes into play. This little plus sign right here. This plus sign, this trigger point, allows us to draw the pattern on the screen from wherever this is. Wherever the voltage or whatever passes this plus sign is where it'll grab it and where it'll start displaying it on the screen. So that allows me to move it horizontally on the screen like I just did. I can just click and drag, move it around. If I move it outside the pattern, watch what happens. It's gone. Oh, there it is. Oh, no, now it's gone again. Oh, there it is. Oh, there it is. This is a pulse. It's actually a fuel injector simulator I'm looking at, but it's a pulse, so it doesn't happen every time where the screen happens to be right in the middle around the one place. Depending on how that screen is refreshing, it might not catch it. So that's where that trigger really comes in handy. So if you have a problem getting a picture on the screen, you want to definitely have that trigger on, be able to catch it. So if I move that trigger up to somewhere within that voltage pattern, it catches it on the screen every time it pulses. I could move it up here too, and it would catch the top part of the screen. If I look on the right-hand side here underneath where it says slope, the squiggly line, notice how it's going top left to bottom right. That means it is on a negative slope or a falling slope. It's catching that on the way down. If I click it again, it goes to a rising slope or a positive slope, and it catches it on the way up. That's all it does. Is it catching it up, or is it catching it on the way down? So in this case, I want it on the way down, and I want it on the bottom. So I catch it as soon as it pulls down. I want to be able to catch that signal. All right, so that is a fuel injector. And that is how I set that up. Notice how it sets up a little bit differently. All I had to do is just change my settings. Let's measure this real quick. So I can go over, make my measurements. Got 15.8 volts in. So in this case, I'd be back probing at a fuel injector, checking the voltage going in. 15.8 volts in this case. To turn on a standard gasoline fuel injector, we need a pull down to ground. So we see down here, we should see pretty close to 0 volts. It is negative 0.1. That is pretty darn close to 0 to me. So we see it pull down to ground. It pulls down to ground for a certain amount of time. So we're going to do a real quick measurement here to see how long that injector pulse width is. So from there to there, that is 1.67 milliseconds is how long my injector commanded on time is. As the injector is open, it has a coil. That coil is storing all that electricity that's coming inside as it's open. So when that coil is released or it closes, all that electricity goes back into the circuit. So we'll see a spike. So if I go over here, top of the spike, I am seeing 28.9 volts, 15 in, 28.9 out. So we should see some form of spike depending on how the vehicle is wired, depending on how the injector is wired. Will depend on how big that spike is. This really isn't getting into the details of the component. This is just, let's see how to use the different functions on the scope, right? So I got one more pattern for you, and we'll just walk through that real quick. We'll do a 2-channel pattern. All right. Don't really see a whole lot going on there, do you? I don't. I certainly don't. I'm going to pull this up a little bit more so I can see what's going on. All right, so I don't see a lot going on. So let's change my settings again. I want a 50 volt scale. Let's go down to, let's say 10. That looks a little bit better. How about we'll go down to 5? Okay, we can go down to 5. There we go. So at 5 volt range, we get this type of signal looking right here. So let me pull that down a little bit. There we go. I want to be able to catch this and trigger it. So my trigger is up off the screen, it's saying right here. I got a little warning message earlier. So I'll just pull down this arrow to get my trigger there. Now I can see I have a little drop coming down. I want to get a little closer this way. I want to see what's going on, spread this out, get a little bit closer horizontally. So we'll call that our sweep. So I'll come down. I know this is pretty fast, so we'll go down to say 200 microseconds. Okay, there we go. 200 microseconds, I'm going to slide this over a little bit. There we go. So now I can see channel 1 of my pattern anyway. I know this is a 2-channel pattern in here. So I'm going to hook up. I have my second channel hooked up, so I'm going to turn that on. Okay. Turn the filter off because we don't want the filter. Now, in this case, the last time I was in here, I was using an amp probe on this channel. So it's set to an amp probe. So we need to change that to a voltage probe. Okay. And we also see that is also set to 5 volts as well. Now, why am I not getting a signal? I should be getting a signal off of this, by the way. All right. Oh, I got to plug it in on the other end. Yeah, so you also need to plug in the scope leads to the scope. That helps too. So let's do that.
Make sure that gets plugged in there. That's what happens when we take things out of the dock every once in a while. There we go. There's my channel 2. That's what I was looking for. Got to do that process of elimination every once in a while. Diagnose your own diagnostics sometimes, right? Okay, so here we go. Got channel 1, got channel 2, got it hooked together. This is a CAN bus pattern, right? In order to check CAN on a vehicle, you need a high-speed scope because of how fast the data is and how small the glitches can be in order to give us a problem. So as we see on CAN, CAN is a nice standard, so it makes it easy to remember what we're supposed to be seeing on the screen. So let me take number 1, put it over there. Number 2, put it on one of these pulses. All right, so you see we have 2 states of the signal. We have this flat line, they call that idle state, where it's not transmitting anything. And then we have these blocks and packets where it's transmitting the data. On a CAN, when it is flat, we should see 2.5 volts, give or take, really close. So we're 2.388 and 2.385. That's very close. When it transmits, it's going to go up by about a volt, volt and a quarter, come down by about a volt, volt and a quarter. So that's around about a volt on both sides. We're pretty good there. Want to see flat tops, flat bottoms. If it ever shorts the ground, you'd see it come down here. That's on the bottom, 0 volts. 5 volts to be up here, 12 volts to be off the screen. Any of those things is bad. Let's take a look at this little pulse right here. How long does that one little data transmitting bit go? So let's pull that in like that. And that's close enough. How long is this distance right here? I am looking at 1.75 microseconds in time passing. That is less than 2 millionths of a second of data right there that we're able to read with a scope. You cannot catch that with a meter. The meter, as we saw before, the digital meter does not react fast enough. You would not catch a millionth of a second glitch in order to do that, right? That's why we need a scope when we get to networking, when we get to things that could be tiny fractions of a millionth of a second of a glitch. That's why you need a scope as well. And as you can see, we can go through and we can adjust it as needed. Now, real quick, instead of doing this manually, if we have a snap-on tool, all snap-on tools with scopes also have our guided component test, which is in there. And that is over 5 million tests for different components on a vehicle. So let me load my 2012 BMW that I have right here as a simulator. 328i and 52kp, right? Engine. All right. So once we load into a system on a vehicle, it'll have all the components that we can test on that vehicle. I was just checking the CAN bus. I'm already hooked up to a CAN bus, so let's go to CAN bus. If I want to know how it works, I can go into component information. All the components will have component information on them. In this case, I just want to go straight to a test. I'm going to signature test it. Gives us a known good pattern right there. Looks an awful lot like what we were just looking at, right? Tells us how to hook up. Hook my yellow to the CAN bus high, green to CAN bus low. In this case, I think I'm opposite, but that's okay. Going to hit view meter. And then the meter will do all the setup for you. So I have my voltage going here, and then I have my time down here. If I flip these around, let me do my CAN high, CAN low like it just asked me to do, and that'll capture my signal a little bit better. There we go. So there's my signal on the screen. It's set up my sweep time. It's set up my voltage. It's set up my trigger point. Everything was set up for me. I didn't have to memorize how to set anything up. And like I said, it's over 5 million tests in here, covers over 40 different makes. It goes all the way back to 1981 that got a component test function in there. So yeah, having a scope is a necessity. Absolutely. I hope you would agree at this point in the presentation that yes, I need a scope to test these things on vehicles, these little tiny glitches that I need to catch. But to make it even better, where you don't have to remember how everything works on every single car that you're ever going to test, we have a wealth of information inside a snap-on scope guided component tester, right? And with that, that is our time here today. So make sure you tune in for new diagnostic content every week. We will be premiering a new video every Wednesday at 7 p.m. UK time. So make sure you check it out
on the YouTube channel. If you're watching, well, of course, you would be watching this on YouTube, but make sure you subscribe, thumbs up, ring the little notification bell so you know anytime we post new content. And it's youtube.com/Snap-on Diagnostics UK. With that, time for questions. If you have any questions, just feel free. Once again, if you're watching this on a premiere, just leave it in the live chat and we'll answer those. Otherwise, leave a comment under the video and we will get to those as we monitor those comments as well. So I'd like to thank you for taking a little bit of time out of your day to learning a little bit more about how you might be able to be more efficient at diagnosing vehicles using some of the information that we've given you today. Hopefully we'll see you next week. Hopefully you can watch and see you on any of our other videos. Have a good week, have a good night, and take care.